Welcome back for another deep dive. Today, we're going on kind of a fascinating journey, exploring the chemistry that's hidden all around us. I mean, in plain sight, really. We're going to be talking about mixtures and solutions and pure substances.
Things you encounter every single day.
Exactly. I have
Yeah.
to admit, some of those terms from chemistry class feel a little bit, well, let's just say I haven't thought about them much since high school. But I'm sensing this deep dive is about to change that.
Absolutely.
So let's start with something I think we all encounter on a daily basis: mixtures.
Mm.
What exactly makes something a mixture in the scientific sense?
That's a great question. A mixture is really just a combination of two or more substances where each substance keeps its own unique properties.
Okay, so it's like a team where each player brings their own special skills to the game.
It is, exactly.
Okay, that makes sense.
Yeah.
So if I think about like making a salad, that's a mixture because the lettuce and tomatoes and cucumbers are all distinct ingredients, right? But they don't change their fundamental nature just by being in the salad bowl together.
Mhm. Exactly. The lettuce is still lettuce, the tomato is still tomato, and so on, and you can separate them back out if you wanted to.
Okay, I'm with you so far. But there are also these terms like homogeneous and heterogeneous mixtures, right? Is that about how well the ingredients are mixed?
You're on the right track. Homogeneous mixtures are those that are uniform throughout. It means that the composition is the same no matter where you sample it. Think about sugar dissolved in water. Every sip tastes the same level of sweetness because the sugar molecules are evenly distributed.
So it's like my morning smoothie.
Mm.
I always make sure to blend it really well. So it's nice and smooth and consistent.
Mm.
I guess I'm aiming for a homogeneous mixture every time.
Exactly. You're a chemist in the kitchen.
There we go.
Now, heterogeneous mixtures, on the other hand, have visibly distinct parts. Think about sand and iron filings. You can easily see the individual components, and they retain their individual properties, even when mixed.
Okay, that's a good point. So it's not just about how well things are blended, but whether the different substances actually kind of merge at a molecular level.
Precisely. And this leads us to a special type of homogeneous mixture that we call a solution.
Solutions. Okay, I feel like we're getting into more specific territory now.
A solution is a type of homogeneous mixture where one substance, called the solute, dissolves completely into another substance called the solvent.
So back to my morning coffee. If I stir sugar into it, the sugar is the solute and the coffee is the solvent.
You got it. And because the sugar dissolves completely, you get a smooth, evenly sweet coffee solution. Every sip is consistent thanks to that homogeneous mixture.
Now, I'm thinking about all the solutions I encounter every day without even realizing it. It's kind of mind-blowing. But you mentioned something about solutes dissolving completely. Is there a limit to how much a solute can dissolve?
That's a sharp observation. And it leads us to the concept of solubility. It's the maximum amount of solute that can dissolve in a given amount of solvent at a specific temperature.
So there comes a point where no matter how much more sugar I try to stir into my iced tea,
Mhm.
it just won't dissolve anymore.
Exactly. You've reached the saturation point. The solvent can't hold any more solute at that temperature.
Okay, I'm starting to feel like a chemist. But how do we measure how strong a solution is? Like how much solute is packed into that solvent?
That's where the concept of concentration comes in. It essentially tells you how much solute is present in a given amount of solution. There are different ways to express concentration, but one common method is mass by mass percentage.
Mass by mass percentage. That sounds a bit technical. Could you break that down for me?
Absolutely. It's actually simpler than it sounds. It's the mass of the solute divided by the total mass of the solution expressed as a percentage. For example, if we have 25 grams of salt dissolved in 100 grams of water, the total mass of the solution is 125 grams. The mass percentage of salt would be 25 grams divided by 125 grams multiplied by 100, which gives us 20%. So we have a 20% salt solution.
Okay, I'm following. So a higher percentage means a more concentrated solution.
Exactly. Think about strong coffee versus weak tea. The strong coffee has a higher concentration of coffee solutes, making it more intense in flavor.
So dilute solutions have a lower concentration, and concentrated solutions have a higher concentration. It all comes down to the ratio of solute to solvent.
You've got it. And here's something else to consider. We often think of solutions as liquids, but they can exist in other states of matter too.
Wait, really? Solutions can be solid or even gases.
Absolutely. Think about alloys like brass or bronze. They're solid solutions where different metals are mixed together at the atomic level, giving them unique properties like strength and durability.
Wow, so the metal spoon I use to stir my coffee is technically a solution. That's pretty cool.
And don't forget the air we breathe. It's a gaseous solution, a mixture of nitrogen, oxygen, and other gases that are evenly distributed.
So solutions are way more diverse and common than I initially imagined. It's like a whole hidden world of mixtures happening right under our noses.
Yeah.
Before we move on, is there anything you'd like to add about solutions or any key takeaways you want to highlight for our listeners?
I think the key takeaway here is that solutions are a fundamental part of our world. They play a role in everything, from the food we eat and the drinks we enjoy, to the materials we use, and even the air we breathe. Understanding the concept of solutions helps us appreciate the complexity and interconnectedness of the world around us.
I completely agree. It's like we've unlocked a secret code to understanding so many everyday phenomena.
Okay, now I'm curious, what happens when things don't dissolve so perfectly? Is that where those other types of mixtures come in?
You're exactly right. When substances don't completely dissolve, we enter the realm of suspensions and colloids.
Okay, suspensions and colloids. These are the mixtures where things get a little, well, messier.
You could say that suspensions are heterogeneous mixtures where the particles are large enough to be seen with the naked eye and they tend to settle down over time.
So like muddy water, you can see the dirt particles swirling around, and if you let it sit, the dirt eventually sinks to the bottom. Perfect example. The dirt particles are suspended in the water, but they don't dissolve. And because they're relatively large, you can actually separate them out by filtration.
So you could use like a filter to remove the dirt particles and get clearer water.
Exactly. Think about a coffee filter or even a water filter. They're designed to trap those larger suspended particles. Now let's move on to colloids, which are a bit trickier.
Trickier? How so?
Well, colloids are kind of like the in-betweeners of mixtures. Their particles are smaller than those in suspensions, so they don't settle out over time. But they're not fully dissolved like in a solution.
Okay, so they're floating around in a sort of limbo state. Can you give me like a real-world example?
Think about milk. It looks homogeneous, smooth, and white, but it actually contains tiny droplets of fat dispersed throughout the water. Those fat droplets are small enough to remain suspended, giving milk its opaque appearance.
So milk is a colloid. I never would have guessed. What's fascinating is that it doesn't separate like the oil and vinegar in salad dressing, which I'm assuming is a suspension.
Spot on. And this difference in particle size leads to some unique properties in colloids. For example, colloids exhibit something called the Tyndall effect.
The Tyndall effect? That sounds intriguing.
It describes how light is scattered by colloidal particles. Have you ever noticed how a beam of sunlight becomes visible when it shines through a dusty room?
Oh yeah, it's like those beautiful rays of light you sometimes see streaming through windows.
That's the Tyndall effect. The dust particles, which are colloids, scatter the light, making the beam visible. And this effect explains other phenomena too, like why the sky is blue.
Wait, the blue sky is caused by the Tyndall effect. How does that work?
The tiny particles in the atmosphere scatter the shorter wavelengths of sunlight, which happen to be blue and violet, more effectively than the longer wavelengths. So when we look at the sky, we see that scattered blue light.
That's incredible. I never realized colloids were responsible for such beautiful sights. But how are colloids different from solutions and suspensions when it comes to like separating them out?
Great question. Solutions, as we discussed, are stable and can't be separated by simple filtration. Suspensions, on the other hand, are unstable, and their larger particles can be filtered out. Colloids fall somewhere in between. They are stable, meaning the particles don't settle down over time, but their particles are too small for simple filtration.
So how do you separate the components of a colloid if filtration doesn't work?
There are other techniques like centrifugation, which spins the mixture at high speeds, forcing the denser particles to separate out.
So colloids are a bit more complex to handle, but they're also incredibly versatile. We've talked about milk dust and even the atmosphere. It seems like colloids are everywhere.
They really are, and they play a crucial role in many everyday products and processes. Think about paint, which is a colloid of pigment particles dispersed in a liquid medium, or gelatin, which is a colloid of protein molecules in water.
Wow, colloids are far more prevalent than I realized. It makes you appreciate the intricate chemistry that's woven into our everyday lives. Before we shift gears, are there any key takeaways about suspensions and colloids that you want to emphasize for our listeners?
Absolutely. I think the main point to remember is that the behavior of a mixture, whether it's a solution, suspension, or colloid, depends on the size and nature of the particles involved. And this difference in behavior affects how we interact with and utilize these mixtures in various applications.
That's a great point. Now, I'm curious about the building blocks of these mixtures. Can we dive into the world of pure substances and talk about the elements and compounds that make up everything around us?
Absolutely. Let's shift our focus to the fundamental building blocks of matter, Pure substances. These are the substances that have a fixed composition and consistent properties throughout.
Okay, so pure substances are like the elemental ingredients of chemistry.
Right.
No pun intended. But seriously, I remember learning about elements and compounds back in school. Can you remind me what makes them different?
You're right. On the money. Elements are the simplest, most fundamental, pure substances. They cannot be broken down into simpler substances by any chemical means. Think of them as the letters of the chemical alphabet. We
Yeah.
have elements like gold, oxygen, carbon, each with its unique set of properties.
And compounds are like the words we form by combining those letters.
Right.
Exactly. Compounds are formed when two or more elements chemically combine in a fixed ratio. Water, for example, is always composed of 2 hydrogen atoms, and 1 oxygen atom that's H2O, table salt, or sodium chloride is another common compound formed from sodium and chlorine.
So the key difference is that elements are the simplest building blocks, while compounds are formed by combining those elements in specific ways.
Precisely. And what's fascinating is that compounds have properties that are distinct from the elements that make them up.
Can you give me an example of that? Think about water again. It's a liquid at room temperature, essential for life, and it can dissolve many substances. But its components, hydrogen and oxygen, are both gases at room temperature. Hydrogen is highly flammable, and oxygen is necessary for combustion. So by chemically combining these two elements, we create something entirely new with its own unique set of properties.
That's pretty incredible. It really highlights the power of chemical bonding.
Yeah.
It's like taking 2 simple ingredients and creating a whole new dish with a completely different flavor profile.
That's a great analogy. And there's a fascinating experiment that illustrates this concept beautifully. It involves mixing iron filings and sulfur. You just combine them, you have a mixture. You can still see the individual iron and sulfur particles.
But if you heat them up, something magical happens.
Exactly. A chemical reaction occurs and a new compound is formed, iron sulfide. This compound has completely different properties than either iron or sulfur alone. It's no longer magnetic like iron, and it has a different color and texture.
So by heating the mixture, you're essentially forcing those elements to bond together, creating a new substance with its own unique identity.
Exactly. And this highlights the crucial distinction between mixtures and compounds. In a mixture, the components retain their individual properties, while in a compound, the elements combine to form something entirely new with its own distinct characteristics.
Okay, this is really helping me to understand the fundamental differences between mixtures and pure substances. But you mentioned earlier that there are different types of elements. Can you remind me what those are?
Of course, we classify elements into 3 main categories: metals, nonmetals, and metalloids.
Okay, I vaguely remember those terms, but can you give me a quick refresher on what distinguishes them?
Metals are typically shiny, malleable, which means they can be hammered or shaped without breaking, and ductile, meaning they can be drawn into wires. They're also good conductors of heat and electricity. Think of elements like gold, silver, copper. They all exhibit these metallic properties.
And nonmetals are kind of the opposite.
Right. Exactly. Nonmetals are typically dull, brittle, and poor conductors of heat and electricity. They often exist as gases at room temperature, like oxygen and nitrogen. Other examples include carbon, sulfur, and chlorine.
So it's like a spectrum with metals on one end, nonmetals on the other, and then we have the metalloids in the middle.
Right, you got it. Metalloids have properties that fall somewhere between metals and nonmetals. They can be shiny or dull, and their ability to conduct heat and electricity varies. Silicon, which is used in computer chips, is a classic example of a metalloid.
This reminds me of like the periodic table where all the elements are organized based on their properties. It's amazing to think about the vast diversity of elements that exist in the universe and how they combine to form all the different compounds and materials we encounter.
It is truly remarkable, and understanding these fundamental building blocks of matter is essential for comprehending the chemistry that governs our world.
Well, it's been an absolutely incredible journey exploring the world of mixtures, solutions, and pure substances. You know, it really makes you appreciate the hidden chemistry that's happening all around us every single day.
I couldn't agree more. And I hope this deep dive has sparked a renewed curiosity in our listeners about the fascinating world of chemistry.
I think it has, and I have a feeling we'll be uncovering even more chemical wonders in future episodes.
Definitely. There's always something new to explore.
So until next time, keep on experimenting, observing, and asking questions.
Yeah.
Because the world of chemistry is full of endless possibilities.
That's right.